All right, welcome. This is Dr. Morton, and I'm going to try and cover Chapter 13. This is the video for Friday. So if we first look at the syllabus, we see that November 4th, that's Friday, although today actually is Sunday the 6th, so so I'm doing this a little bit late. Anyway, so we were supposed to cover Chapter 12. Well, we've already finished Chapter 12. So I'm going to skip on to 13, and that'll I'll probably do this. We'll cover this. I'll probably cover Chapter 13 today. We'll see. Maybe I'll just do a little part of it, and we'll do the rest on Monday with a second video. All right. Okay, so let's go ahead and look at the book. So here is our here's the book, and you can see that. What we're doing here, we're looking at how you can take a state table with some redundant or equivalent states and reduce them and get down to a smaller state table. So the learning objectives, I want you to be able to state what class of sequential design problems can we consider for redundant states. And the answer is that problems that have a fixed number of inputs and then they reset to the beginning. So like they input four inputs, and then they reset. 4 inputs and they reset, or 8 inputs, or 7, or 6, or 10, or whatever. And so that's a class of problems where we can look for redundant states. The other thing that we can do is, and then we should be able to actually identify redundant states and eliminate them, and then substitute in one state for all the redundant states, for all their equivalent redundant states. All right, second thing is to be able to demonstrate reducing a state table by eliminating equivalent states. And for that, we need either an implication table or distinguishing sequences. And so we'll look at that. All right, so some terms. State reduction. This just means figuring out a way to combine some states so that we don't have to have as many states. Redundant states are states that in a problem where we input a fixed number of inputs and then reset. And in that, we're looking for states that have the same next states and the same outputs. And in that setting, we can just substitute in, if there's 2 such states, then 1 state is sufficient. If there are 3 such states, then we just need 1 state. And so we'll substitute that one state in for the other states. And then we'll re-examine it and see if there are some new additional redundant states. Equivalent states, we'll use that distinguishing sequences are an implication table. And that's what these two. The implication table is just a way to identify these equivalent states, and a distinguishing sequence is a very important concept that also has a lot of play when we are trying to develop tests for our sequential designs. And let me just read the definition. So this is a technique using a sequence of inputs starting from a given state to differentiate between different states. It can be used to identify equivalent states when there's no distinguishing sequence that can be found that separates between 2 states. So if you can't find a distinguishing sequence, what that typically means is, though, those 2 states are equivalent. All right. So you should read through the introduction, state reduction. Why is it important to do state reduction? Well, obviously, if you can shrink your state table, you may get by with fewer flip-flops and certainly less hardware. So that's the whole idea. And you simplify the problem, and oftentimes, if you're able to simplify the problems, it means that you can grasp the problem mentally a lot better. You can kind of wrap your head around it when it's a simpler problem, usually. There might be exceptions to that. But okay, so for instance, here's a busy state table. Now notice I have not put in any of the x primes or z primes. All I have are I've only shown the x's and the z's. So where I have blanks, you can assume that the x here would be an x prime and the z would be a z prime. Or x would be a 0 input and z would be a 0 output. Normally we should just leave these all blank and declutter it completely, but I kind of put these on here for training wheels, and then later on we took them off. All right, so we start in state S0, and we go on a x equals 0 we go to S3, but on an x equals 1 we go to S6. We output, in either case, we output z equals 1. From S3, if we get an x equals 1, we go to S1 and we output z equals 1. And from S3, if we get a 0 for X, we still output Z. And then from S1, I'm not really going in order here. They're kind of mixed around, as you can see. From S1, on a 1 we go to 3, on a 0 we go to S2. In this case, we output Z equals 0. But here, we output Z equals 1. And then on S2, if we get a X is 0, we output a Z is 0, and we go to S4. And if we get a 1, we output X equals 1 and Z is 1. From S5, if on a 1, we output a 1 and go back to S2. And on a 0, we output a 1 and go to S3. And then, let's see, yeah. So that basically, I think we covered everything now. Yeah, maybe, yeah, I don't know if we covered S4 or not. If we're in S4, yeah, we go here on a 0 and output a 0 and go here on a 1, output a 1. Okay, so that's the problem. Now, we're not really explaining what this problem does. That's just the state graph. And then here's the state table. Now, if you look at the state table, you see, say in S6, our outputs are 0 and 1, and we go to S0 and on X equals 0 and S3 on X equals 1. Let's see if we can find any. So in this case, okay, so you can see this is kind of confusing. We can inspect this table, but just on inspection, I don't see any obvious examples where we have where we can sort of see how we could draw some equivalent states. So let's look at the technique of doing distinguishing sequences. Now this is kind of tricky. Later on, we're gonna go back and look at a problem where we have a fixed number of inputs and we can look for redundant states. That makes a lot more sense. This one is a little harder to see, but let's see if we can work through this. Okay, so first off, we're gonna group all the states into two groups based on just a single, just one input. Okay, so if we get one input, then we want to look at the outputs. So we have on just one input. Say if we're in S0, depending on the input, we're going to see X. We're going to see the output Z is going to be 1 in both cases. That's also true in S3 and also in S5. So we can go down here and we can group S0, 3, and 5 all in one group because their outputs are always 1 regardless of the input. Now, how about S1? Well, on one input, these outputs are always 0, 1. 0, 1 for S1, 0, 1 for S2, 0, 1 for S4, and 0, 1 for S6. Okay? So we have S1, 2, 4, and 6 give us the same outputs. Let's see. Did I do this wrong? Oh, yeah, that may be a mistake because the outputs are 0, 1. Yeah, all right. That is a mistake. So I can't fix this. I'm going to have to submit a request to get that fixed. Okay, so let me show you what the corrected table should look like. It won't be changed in the book probably for a while. But here's what it should look like. So you see the columns here should be 0, 1, columns here should be 0, 1, 0, 1, 0, 1, 0, 1 instead of instead of, you see here, it's 0, 0, 0, 0, 0, 0, 0. So that was wrong. Yeah, it's funny. You can see it here. Oh, no, you can't. Okay, so you can see it here. Anyway, hopefully you can see that. All right. So now, so we're able to, so that accounts for S0, 1, 2, 3, 4, 5, and 6. So that's all our states. So all our states are able to be separated because they have this pattern of outputs into two groups. But that's based on just the first input. Now, the first input, of course, changes them to a new state. Then you have to look and see what their next outputs would be. So, for instance, from state S0, we go to state S3. From state S1, we go to state S2. We have to look within this group. So let's look at what happens with S0, 3, and 5. Well, so 0 goes to 3, 3 goes to 5, and 5 goes to 3. So it turns out, after the next input for x equals 0, they stay within the same group. Remember, our group is 0, 3, 5. So 0 goes to 3, that's in the group 0, 3, 5. 3 goes to 5, that's in the group 0, 3, 5. And 5 goes to 3, so that's in the group 0, 3, 5. What about if x equals 1? Well, 0 goes to 6, 3 goes to 1, and 5 goes to 2. So that actually is still that's all in the same group too, but it's the other group of 1, 2, 4, 6. Okay, so that's the other group. So this is group 1, 2, 4, 6, and 0, 3, 5. So for for two inputs, we wind up in the same group, either this group or this group. And that's for all three of the states in this group. Okay, what about this group? So we have to look at 1, 2, 4, and 6. So for an input of so here's 1. If we get if our first one is a 0, we're going to S2, and in S2. We're still in group 1, 2, 4, 6. For S2, on a 0, we're going to S4. That's still in 1, 2, 4, 6. For S4, we're going to S1. Okay, that's still in 1, 2, 4, 6. And for S6, we're going to S0. Oh, okay, that's a problem. Notice for X6 on a x equals 0, we're not going to either 1, 2, 4, or 6. We're going to 0, which is in the group 0, 3, 5. So that's in the other group. So that means we have to separate out the x6. And then for x equals 1, S1 goes to 3. That's in the group 0, 3, 5. For 2, we're going to 5. Okay, that's in the group 0, 3, 5, so that's fine. For 4, we're going to 5, so that's in 0, 3, 5. And for 6, we're going to 3. So that would be okay for x equals 1, but for x6, it's not okay for x equals 0. That puts us in a different group. It doesn't matter which group you get in, as long as all of these have to be in the same group to show that there's no distinguishing sequence. But in this case, there is a distinguishing sequence for x6, for S6. So now we have to separate out S6 out as its own separate group. Okay? So now we do this. Okay, so now when we do this, for two outputs, 0, 3, and 5 have no distinguishing effect. These are all in. Let's see, which was it? 0 goes to S3. Yeah. So on 0 they stay in 0, 3, 5, and for 1 they stay in 1, 2, 4, 6. So either way, that's okay. But this group, the S6 ones don't. They don't work correctly. They have a distinguishing sequence. So now we create their own group. So now we have three groups. We have 0, 3, 5 is one group. 1, 2, 4 as another group, and S6 as a group by itself. As soon as you're put in a group by yourself, then we can forget about you because we don't have to worry about a distinguishing sequence because we already have a distinguishing sequence now for S6, and that is you put in two inputs, a 0 or a 1, and then a 0, or a 0 and a 1, and you're gonna 0 and 0, and you're gonna see that S6 is different. All right, what about where do we go from here? Well, so now we have so now we have this. Now we're going to look at 3 inputs, and so this starts to get confusing, I admit, but it turns out there's an easier way. Okay, so that's a good thing. But if we did 3 inputs, so for S0, if we do, let's say we do a 0, that puts us in S3, so we already know that. And then if we do, and then for 3, that puts us in 5, and 6, 5, that puts us in 3, so that's good. And then we looked at 1, and that put us in the other group, yeah, but now there's a problem. Notice S6 is no longer in the group 1, 2, 4, 6. It's all by itself. So that means S0 is going to have a problem. When we look at x equals 1, S0 goes to S6, which is not in the same group as S3 and 5. S3 goes to 1, and S5 goes to 2. So those are okay. But going to 6 is not okay because 6 has been kicked out of that group. So now we have a distinguishing sequence for x0 with our inputs. So now we have so now we're going to take S0 out of this group, and right here this distinguishing sequence is a problem with 3 inputs, and so now we have another group. Okay, now this is, and we can keep doing this. It gets tedious and somewhat difficult. But this is actually the hard way to do it. So if you keep on reading down, here's what we have for our groups right now. We have S0 by itself, S6 by itself, and 1, 2, 4 by itself, and 3 and 6 by itself. Okay. And then it turns out if we keep going, we can never distinguish between 1, 2, and 4, and we can never distinguish between 3 and 5. So we assume these are equivalent groups, and that is if we keep doing inputs, no matter how many inputs we do, these always stay in the same groups. So we say there's no distinguishing sequence for these, therefore they're equivalent. So now we can substitute S1 in for 2 and 4, and 3 in for 5, and we just have then 4 groups: 0, 1, 3, and 6, and then we probably would renumber them and so that we have 0, 1, 2, 3. Okay, but in any event, we've been able to reduce, we get rid of 3 groups here, and you can see we substitute in then 1 for 2 and 4, and 3 for 5. So there's 2, we put in, we get rid of this, 4 we get rid of that, and 5 we get rid of that, and substitute in everywhere else, and boom, there we have it. Okay. So now if you look at the state graph, we can redraw the state graph, and this is what it looks like now. Sometimes you can see this is a lot easier. This state graph here is a lot easier to grasp than this state graph. That's a lot harder. All right, so anyway, so that's one of the benefits of simplifying, reducing our equivalent states. We can come up with a simpler problem, and we only have 3 nodes. Now, normally what we do is start over and renumber these nodes instead of having 0, 3, 1, and 6. All right. Now, the nice thing, there are a couple other ways you can do this. One is much easier than the one we just did, and we can modify the one we just did by this new approach. So let me just so you see this paragraph here. Okay, so you can see that this analysis could become tedious, but fortunately there's an easier way. At each step, we only have to verify that for the new input x equals 0, that all the next states for each group only fall within one of our defined groups, not necessarily the same group that we are testing. And if the next states from a group for x fall into the 2 distinct groups, then they must be separated and cannot be equivalent. And then we can repeat for x equals 1. And if in either case we get a result that's not within a single defined group, we have a distinguishing sequence. So that's kind of what we did. So let's try this approach and see what we get. Okay, so our first analysis, we can group with one input into the groups of 0, 3, and 5, and 1, 2, 4, and 6, based on their outputs of with x equals 0 and x equals 1. Now we look at the first group, 0, 3, 5. For x equals 0, the next states are 3, 5, 3, which are all in one group. For x equals 1, the next states are 6, 1, 2. These are all in the 1, 2, 4, 6 group, so they're not distinguishable. Now we consider S1, 2, 4, and 6 in the same way. For x equals 1, the next states are all in the same group, but for x equals 0, the next states are 2, 4, 1, and 0, which are not in the same group, so we have to factor out x's. This is what we found when we did the complete analysis above. Now, if we go to the next level of 3 inputs using the same approach, our current 3 groups are 0, 3, 5, 0, 1, 2, 4, and 6. We don't have to consider the group with only one state. For the first group, for x equals 0, the next states are 3, 5, and 3. And for x equals 1, the next states are 6, 1, 2, 6, 1, and 2. But now 6 is not in this group anymore, so now we have to separate out x0. So this gives us 4 groups, 3, 5, 1, 2, 4, S6, and also S0. Yes, that verbiage has to be changed. Okay. Okay, you can see that here we should have S0 semicolon, S3 comma S5 semicolon, S1 comma S2, S4 semicolon, and S6. 4 groups. S0 being one of the other groups that was missing from that statement. All right. So now we can repeat the same analysis on the 2 groups with more than one state. So that would be S3 and 5 as one group that's got 2 states still in it, and S1, 2, and 4 that have 3 groups. Well, so for 3 and 5, the next states for x equals 0 are 5 and 3, and for x equals 1, they are 1 and 2, which are both in the same. The results are all in the same group, different groups, but in the same group. For both 0, it's in the group of 3, 5, and for 1, it's in the group of 1, 2, 4. So that's okay. And for x equals 0, the group 1, 2, 4 are in 2, 4, 1, so that's okay. And for x equals 1, it's in 3, 5, 5. So that's all in the same group. So since there are no other outliers, we can conclude that the current groups are equivalent within each group. So S3 and 5 are equivalent, and S1, 2, and 4 are equivalent. S0, of course, stands by itself, and S6 stands by itself. So now we can substitute in S1 for S2 and 4, and S3 for S5. And of course S0 will be itself, and S6 will stay itself. And that gives us our reduced state table, where we have crossed out 3 states, and we're left with these, and here's our new graph, and so forth. All right, now we can also do this with an implication chart. I'm not going to spend a lot of time on this. I just want to expose you to it a little bit so you have the idea. So we take the non-reduced state table, which we started with before, with 7 states, 0 through 6, and we make this little checkerboard square. Now notice we don't start with S0 up here. We start with S1, 2, 3, 4, 5, 6, and here we start with S0, 1, 2, 3, 4, 5. We don't put S0, S6 down here. We don't put S0 up here because we don't want to compare S0 to itself, because of course it would be identical. And we don't want to compare S6 with itself because it would be identical. So we compare S1 to S0, S2 to S0, S3 to S0, S4 to S0, S5 to S0, and S6. Now it turns out that we immediately know that 1 and 0, 2 and 0, 4 and 0, and 6 and 0 cannot be the same because they have different outputs. All you have to do is go back and look at this table. So S0 has outputs of 1 and 1, but 1, 2, 4, and 6 have outputs of 0 and 1. So we can immediately cross out S1 and S0 cannot be the same, S2 and S0 cannot be the same, S4 and S0 cannot be the same, and S6 and S0 cannot be the same. But S3 and S0 could be, and S5 and S0 possibly could be too. However, note here, how do we check this? Well, let's look back at the table. So if S0 and S3 are the same, then S3 would have to be the same as S5, and S6 would have to be the same as S1, right? So we write that in. S3 must equal S5, and S6 would have to equal S1 if 0 and 3 are the same. All right. So we're not sure if that's true or not. We're just going to write that and see what happens. S5 and S0 could also be the same. If that were true, so here's 0. So 3 and 3 would have to be the same. Well, that is true, right? And then 6 and 2 would have to be the same. All right, so we don't have to write S3 equals S3 because we know that's true, but S6 equals S2. So we just have one condition down here. All right, continuing. How about S1? Well, we can compare it to S2, S3, S4, S5, and S6. And we know it can't be equal to S3 and 5 because we have different outputs. So then we write the conditions in. So S1 would be the same as S2 if, so 1 and 2, if 2 and 4 are the same and 3 and 5 are the same. 2 and 4 are the same and 3 and 5 are the same. Okay? So that's our condition. And then we do the same here and the same here. Here we have identical conditions, so we don't bother with them. And so forth. When we get all done, this is what we have. We have some possibilities. It's possible that 0 and 3 could be the same, 0 and 5 could be the same, 1 and 6 could be the same, 1 and 4, 1 and 2, 2 and 6, 2 and 4, 3 and 5, 4 and 6, and that's it. All right, now we go back through and compare everything again. So we look at these conditions. Could S3 be equal to S5? Well, where's S3? It's here. Where's S5? Here. So S3 and S5. Could they be the same? Possible. How about here? How about S6 and S1? Well, so S6 is here, S1 is here. Okay, still possible. So we don't change this. How about S6 and S2? So here's 6 and here's 2, possible. How about S2 and S4? Here's 2, and we compare 2 to 4, possible. How about S4 and S1? Sorry, S3 and S5. S3 is here, S5 is there, possible. How about 2 and 1? So here's 2, here's 2, where's 2 and 1? 2 and 1, possible. How about 3 and 5? 3 and 5, possible. How about 6, how about 2 and 0? 2 and, here's S0 and S2. Not possible. Okay, so we already know S2 cannot be equal to S0, so we're going to put a cross in here. And then we can check 4 and S1. So where's 4 and 1 is possible. What about 4 and 0? Here's 0, here's 4. Not possible. So this square gets crossed out. How about 1 and 2? Possible. Yeah, 1 and 2, possible. How about 1 and 0? 1 and 0, not possible, so we cross this square out. So now we've crossed out some more squares, and now it looks like this. We crossed out this one, and this one. Right. And we still have these. Now we check it all again. All right. So what about 6 and 1? 6 and 1 is now not possible, so we cross this one out. 3 and 5 was still okay. How about 6 and 2? 6 and 2 is also not possible, so now we cross this one out. What about 2 and 4? Well, 2 and 4, still possible. 3 and 5, still possible. 2 and 1? 2 and 1. So here's, let's see, there's 2 and 1, still possible. And so forth. We go through the whole map, and then we've crossed out some more with these lighter squares. So now we're just left with these. Now we look at it one more time. Can we cross anything else out? And it turns out that we can't cross anything else out. So when we finally can't cross anything else out, we're left with the conclusion that S1 and S2 are equivalent. S1 and S4 are equivalent. And then S2 and S4 are equivalent. And S3 and S5 are equivalent. So now we go back to our little table up here, and we have 3 groups again. S0, 1, 2, and 4 are the same, so we substitute 1 in for 2 and 4, and 3 and 5 are the same, so we substitute 3 in for 5, and S6 is all by itself, and that gives us this reduced state table with this reduced state graph with 4 states. And that is how you do the implication chart. All right, I think I'm going to leave the redundant state exercise for the lecture for Monday. And I think I'll stop with this. So, if we look at what we've gone through here, we've gone through a couple different ways to find equivalent states, and we should get the same results. One is the implication table, kind of that checkerboard cut on the diagonal, or a couple different ways to try and do equivalent states. And when we're doing these, when we're using this distinguishing sequence method, keep in mind that this is it's important to spend a little time reading through and trying to understand how we did this. I didn't do a good job of explaining the hard way to do it. I basically did it the easy way both times. But the hard way to do it is you just put in things and you see what happens, and you look for the ability to tell the difference between these states. And if you cannot tell the difference between the states, then you know that the states are equivalent. They can give you the same results. That same distinguishing sequence is also what we use when we do testing, because when we have a complicated sequential design problem, a complicated state machine, if you will, all we can do is put in inputs and look at outputs. That's all we can do. We can't get into the middle of our state machine and read values. We don't know what the flip-flops are saying, because this is typically all programmed into a single chip, and we don't have the ability to reach into the chip and touch various points inside the chip. If we built it with discrete components, we could do that. But if we do it with a chip, we can't. And so as a result, like a programmable logic chip, like a FPGA. So in that case, what we have to do is we can only put in inputs and look at outputs. So when we test it to see if our state machine is working the way we want to, we have to do a simulation. We have to put in the inputs and see if the outputs are right. And typically doing a totally exhaustive test can be very difficult. If we have lots of inputs, the numbers of input combinations gets very large, and as a result, we may not have the time to run that test on every single device we make. We may not be able to do that. So what we'll do a lot of times is we'll use these distinguishing sequences to at least check a few things. We'll put it into a known state by using our distinguishing sequence, and then we'll apply one additional input, and then we'll run our distinguishing sequence again and see if we got to the state we thought we were supposed to get to. All right. Well, that's pretty much what I wanted to cover for today. I encourage you to read through the textbook as you do this, because it is a little tricky to understand. I may need to rewrite these passages someday, and I certainly want to correct a couple of errors we found. But it is challenging and a little bit confusing to work through this. All right. With that, we'll quit.